So here we may see that in the frequency response characteristic, our gain is stable up to the cutoff frequency, right? This we have seen. So up to the cutoff frequency, the gain is constant. After that, if you increase the frequency, then the gain will start falling. Okay. So this thing we have studied in our AC characteristic. So similarly here we will observe that characteristic. So what is exactly happening? Our gain. So to determine the gain with respect to the cutoff frequency and the open loop gain, we are calling that as unity gain bandwidth. Okay, UGB, and that formula is open loop gain multiplied with your cutoff frequency. Here F naught, you may write FC also. So here A represents your open loop voltage gain and F naught is your break frequency or cutoff frequency, F naught or FC. You can write both the things. But suppose you want to write the alternate formula with respect to the closed feedback gain, okay, and same your bandwidth or your cutoff frequency with respect to the feedback. So here we got, you may write A naught F naught, and similarly it is AF FF. So this is with feedback and this is without feedback. So how do we relate that? So suppose you have to equate that and you have to find out your feedback frequency or frequency with feedback. So it is nothing but the unity gain bandwidth and your gain with feedback, the ratio in between that two. You have to remember this formula. Okay. So because this also carries 1 mark in the 10 marks question of voltage series or some type of amplifier. Okay. Then we already know that AF is equal to, what is the formula for the voltage series amplifier? If you are writing the gain with feedback, we have to relate that A whole divided by 1 plus A beta or AB. Okay. What is B? Feedback your gain of the feedback loop only. Okay. So by this formula, if you relate now this AF value into your previous equation, what we have studied earlier, at here if you use the value of AF, what shall we get? We may get the value like this. So now if we further solve this equation, what do we get? It AA will get cancelled out and FF is related to F naught or the cutoff frequency without feedback, that will be multiplied with this 1 plus A beta term only. You have to remember this factor is very important, 1 plus A beta term. So now we will identify guys how it is important or how the bandwidth with feedback is more beneficial than without that. We may see with an example. Okay. So suppose we have seen that AF, the feedback gain of the series amplifier, which is nothing but A whole divided by 1 plus minus A beta. So this you may get in your voltage series and shunt case guys, this plus minus, that's why it is written. So series case what we are getting the 1 plus A beta term. In shunt case you may get 1 minus A beta term. Okay. So in all the cases, suppose here we are getting with an example. So suppose the loop gain of a circuit we are considering with these values. A is given 100 and beta value is 0.25, and here it has been asked to you to find out the gain value with feedback. So if you manipulate your answer, you may get 3.8. Okay. So now just keep in mind, with the given data we will change only one parameter, and how it is affecting our feedback gain we will see in the next slide. Okay guys. So here one term has been given, L is called as your loop gain. Overally it has been labeled as 1 plus minus L, or you may write overally also A beta term also you may write. So now have a look. Just remember this equation guys. I am going to change only one parameter, that is, suppose the A in spite of 100 it is reducing to 50. So for this case how much shall we get if we will calculate AF is equal to A whole divided by 1 plus A beta we got. For that case of A is 100, we got 3.8. Now the loop gain or the open loop gain is drastically reducing the factor of half. Okay, from 100 to 50. But how much change we got with feedback? The gain value is changing to 0.1. Here the open loop gain is changing to half, but the feedback with gain is changing from 3.8 to 3.7. So this is the reason, guys. You can see that there is not more changes because we have used the loop gain as constant. That's why we are not getting any change. This 25 is fixed, and this is helping us to achieve a stable gain. Okay. So this is the reason we should go for the feedback in the circuit. Negative feedback we have used it here, and we have to use this concept to achieve a stable gain over a wide range of frequency. Okay. Then you just you go through the theory part of the advantages and disadvantages of your feedback amplifier. And shunt type also you have to go, guys. Series type I have explained. Shunt type you just go. Then new topic we are going to start. The new topic is application of op-amp using diodes. This is the third module for you guys. So application of op-amp using diode. Generally we have seen that diode is a non-linear or linear device. Who will answer? What are the devices we can design by the help of or the characteristic of diode? Diode is a linear or non-linear device, guys?
Non-linear.
Very good. Diode is a non-linear device. Okay. Who will answer that? Why do we call this as non-linear?
Does not follow Ohm's law.
Any other answer? Doesn't follow Ohm's law. That is correct, but not exactly correct. Any other answer? Any exponential rise in voltage, current, anything, any word you want to use?
Output is not directly proportional to input, ma'am.
What word you will use that?
Proportionality.
Proportionality, not proportional. Any exponential rise in value, anything? How you are getting your VI characteristic? Like this. Yeah. Tell me. Your diode VI graph will be like this only, no?
Yes, ma'am.
No
This graph is non-linear. So
non-linear. Why we are calling this non-linear? Because
exponentially increases after a while.
yes, after the cut-in voltage or forward voltage, it will rise exponentially, right? When it will cross that 0.6 or 0.7 level, it will rise like that. Okay. So generally by using the diode, we can design the half wave rectifier, full wave rectifier by the help of the 2 diode transformer or by the help of the 4 diode or any bridge we can frame and we can design so. Okay. But we have to take the help of the transformer only. The transformers are so bulky, okay, and the stray losses are also there in the case of transformer. So why do we prefer the diode still to make the amplifier circuit for rectification? So the reason is, if you combine the property of the diode with the help of the op-amp, you may still get the value, but with less cost, and the size also it is minimized, okay, and convenient to use also. So for that sake, after the circuit we can make the rectifiers. In that we can go for the half wave, full wave rectifiers. We can design the peak detectors. We can design the log and anti-log amplifiers. So these are the applications of diode we are going to make by the help of the operational amplifier. Generally I was saying, guys, this is the diode circuit. Okay, So when the applied input voltage V in is sufficient enough to make the diode to conduct, then only we can say that the diode will conduct, right? So V in should be sufficient enough at here 0.7 the cut-in voltage of diode, and V in should be sufficient enough to force that diode to become conduct, and then only we may get this type of rectification, right? But practically if you see, we may not get that kind of exact output voltage with respect to the applied input, we may not get, and there should be some loss. These are the loss. In yellow color you can see that, okay? Because in practically it is very difficult to achieve the V out equal to V in is never possible. That's why what we may do, what we will do, we will just utilize the characteristic of diode by the help of the op-amp. We will exactly trace the same ideal diode concept with the help of the op-amp also we are going to make. So here we can see that the diode can be used in the receiver circuit for demodulation, to rectify or to identify your demodulated signal which we can receive in the AM receiver, okay? So now let's have a look. This is called as precision rectifier. Rectifier is there, but why we are using the word precision rectifier means exactly in the case of the ideal diode, what I have shown you in this first circuit, guys, we are capable of amplifying the same V naught equal to V in by the help of these two circuits. One is op-amp and one is diode. Whether we are able to achieve the same V out with respect to the V in by the help of a single diode or not, or so that what should we do to improve the rectification or to improve in our rectification, that also we will see. Now just have a look, guys. This circuit belongs to what type of configuration, and in what case the diode will work? You just think and tell me. V in is greater than 0 or V in is less than 0, where the circuit will conduct. This circuit belongs to non-inverting amplifier, right? And at the output path we have connected a diode. If the diode will conduct, then only we can say that our path is complete, right? We may get a feedback loop. So when the diode will start to conduct, yes, when V in is greater than 0 or V in is less than 0, or what? Or you want to apply the virtual ground concept also, you may apply. Or simply it just rectify any other voltage. What is the concept of the diode? Unless until the applied voltage is positive, if this end is positive, then only the diode will conduct. Yes or no? Guys, no response from your side, simply you left. When the diode will start to conduct? If the diode will get the forward voltage in front of it, then only the diode will start to conduct, okay? This is the case. If we may get a positive voltage at here, the diode will start to conduct, and then only we may get a complete path, a complete loop we may get. Suppose V in is greater than 0, the diode will conduct or not? How much cut-in voltage the diode possesses? The PN junction diode 0.6 or 0.7 volt, right? So we need that voltage at here to make the diode, because it is the voltage across the diode 0.6 or 0.7. So we need that voltage greater than at here to make the diode to conduct. And if the diode is conducting, we may get a transfer characteristic like this with respect to the V in and your V out. So it is we can see that both are proportional to each other. It means with the change in input, the output is also changing. So if you see the normal working principle of the diode, we may see that if V in is greater than 0, the diode is conducting, so that we are getting V out equal to V in. Suppose the case here B in is less than 0, the diode will not conduct and it will become an open path. Okay, so the diode will not conduct. So the two cases are confirmed. B in greater than 0, diode is on. If B in is less than 0, the diode is off. This concept you just remember. Now directly I am shifting towards the half wave rectifier, guys. Because if we use a single diode in the feedback path, the single diode is not sufficient enough to rectify the signal. Because see, have a look at here. What type of signal we are going to apply? We are going to apply a sinusoidal waveform which carries two peaks, positive peak and negative peak. In both the cases we can configure the B in. Here B in is greater than 0 or positive, B in is positive, which means B in showing some positive voltage which may be greater than 0. Okay, it is obviously greater than 0, the positive part. This negative part, B in is less than 0. So guys, actually in this single diode case, what was happening in the positive half cycle, when B in is greater than 0, it was conducting. Okay, conducting. But when the case is coming B in is less than 0, as per the property of the op-amp, it was saturating in the negative direction. So by the help of this single diode, it was very difficult to bring the diode back to conducting in the positive half, because it will stay at here unless until it won't get any positive high, it will be at here. So it is very difficult to bring out the diode in the high frequency from the negative saturation to positive one. So that in spite of using two diode, what we have used at here, we can introduce two diode concept. Okay, so in this two diode concept, what will happen, guys? Now let's have a look. Simply I am just explaining. First half we are going to apply a positive input voltage at here. Now we have placed two diode back to back, D1 and D2. D2 is in the output path along with pin number 6, and here it is from your 2 to 6, D1 is connected along with your R2, like that only. So D1 and D2, how the position is connected? This is positive, this is negative, this is positive, this is negative. Now I am going to apply a positive voltage at here. Which diode will conduct and which diode will not? If you see, because of a positive potential we are getting at here, B in is positive. It is not going at here, it is bypassing like this. So it will make diode D1 to on. But because this belongs to inverting configuration of op-amp, what we are getting at here, minus of R2 by R1 into how much it is? Voltage at here, we are getting B in. So this negative voltage you are getting at here of this value will make diode D2 to become off, but it is making this diode D1 to on. But even though D1 is on, it is not making a complete feedback path, it is failed to complete the feedback path. So what should be the output? If I will draw the output, in the positive half it won't conduct. So what will happen? In the positive voltage still it is blank, I am not getting any output, I am not receiving any output at here. Now the second case I will show. Suppose the positive half cycle completed, then now B in is negative. What will happen at here? Now which diode will conduct and which will not?
D2 will conduct.
Okay, D2 will conduct, that is correct. Because see, how D2 will conduct, by which principle? D2 needs some positive voltage, right? Yes or no?
Yes, ma'am.
So here, by the principle of inverting op-amp configuration, we are getting a negative voltage, but still what type of voltage we are applying at here? Negative. This negative will become positive, and that will be sufficient enough to make the make diode D2 to conduct, or to make D2 to become on. So that's why here we may get a positive path because of D2. Now the circuit is functioning, and here What type of output we may get now? In the positive half, it was 1 minute, guys. In the positive half, it was blank, but in the negative half, it will conduct. So the waveform will be like this or like this, inverted one. Who will say? Yeah, the waveform will be this one or this one. Solid one or dotted one? Think and tell me.
Inverted one, ma'am.
Any other answer? I'm not saying that you are wrong. Any other answer? Or shall we go with your friend?
Solid one, ma'am.
Solid one. What is the reason for inverted one? Who
Ma'am,
had
if we
answered?
are getting like when Vn is negative,
Mhm.
then only we are getting.
Okay, for solid one, it is your concept. Okay, who answered it is solid one? Name?
Me, ma'am, Abhigya.
Abhigya. What is the reason for the solid one?
Because it's inverting amplifier.
Yes, that is the answer. And some more point I will add it here. It is inverting and negative voltage, so it will positive, no? Getting my point? So the output will become like this only. Already this is inverting amplifier and we are applying an inverted voltage. Inverting and inverting, it will become like this. That's why we may get non-inverted output. Means if you say for with respect to the applied input, it will become inverted. That's why we are getting a positive peak at here. So this is the concept of half wave rectification. But you can see that if we are adding a single op-amp at here, still positive half is blank. It means we are getting half rectification of the input. It is not completely rectified. So that we have to label this as half wave rectifier. So some more cases of it I will just show. Just have a look. Theory will be remain same only. This is the transfer characteristic of your two diode because it is functioning in the negative half only, minus of RF by R1 or minus of R2 by R1. That's why it is showing the peak in the negative quadrant only. Okay, so this is the output for that position. But if you connect in this position diode back to back, this is the transfer characteristic, and I'm just asking you all guys, draw the output waveform for this if the diodes are connected in this way with respect to op-amp. This we will do in your lab classes also, but this is the transfer characteristic of the diode if it is connected in this way. Then how do we achieve a full wave rectification which will give rise to the rectification in the positive half cycle also? That can be achieved by adding one more op-amp as a adder circuit. Okay, if you use that summer circuit, like in the block diagram I can say that half wave rectifier plus one more op-amp to add the two signal. If we will use that, then we may get the full wave rectification. This is the circuit diagram for inverted full wave rectifier, and here I will show you non-inverted rectifier. Both of the circuit you can understand. Actually we are asking in exam question from the circuit itself. What will be the output of the circuit? That time we may not mention that whether it is half wave rectifier or full wave, because all the concepts are coming the application of diode by the help of the op-amp only. Now we will analyze this. Guys, you may practice the output. How do we get the output from the explanation of this one? Okay, this is one homework for you. Just practice this circuit to get the output. Okay, at here let's have a look. This circuit diagram is for full wave rectifier by the help of the two op-amp. Here you can see we have two op-amp, A1 and A2, and by the help of the same two diode only we are using, but additional component is extra op-amp we are using, and that op-amp if you see we are using as a summer. How we are using as a summer? Later I will show you. Okay. So we will analyze the circuit, case 1 and case 2. Case 1. For the case 1, same sinusoidal input we are going to apply. V in, positive half, negative half. Now the case 1, D1 should conduct or D1 should on and D2 is off. Now in which case D1 will conduct and D2 will not? In the positive half cycle. Okay, for the case 1, let's consider D1 is on and D2 is off. If D2 is on, off and D1 is on, what type of circuit we may get? This part is on and this part is broken. Okay, so this part, because you can see that this is not conducting, this part is open, so that's why we have consider this is grounded. Okay, so what is the next simplified circuit? This is the next simplified circuit of the case 1. When D1 is conducting, we may get this path is closed and this, from this to this terminal it is open. Now this is the simplified circuit for case 1. So if this is R, this is conducting, this point will join at here, that's why this is R and R. Now who will say me guys what should be the V0 at here? Look at the circuit. If all R's are equal, all are R only, what should be the V0?
V in.
Very good. Who has answered this?
Abhigya.
Abhigya. Very good, Abhigya. So can you tell me what is the output of the op-amp A1?
Minus V in.
No, with equation you tell me.
Minus R by R V in.
Minus R. So that because this is an inverting operational amplifier, and as per the output voltage equation we have to write minus of RF by R in into V in. Okay, so here we can see RF is R and R in also R, so that we are getting minus B in at here. So minus B in is the input for the second operational amplifier. So what is the output now? Who will say except Abhigya? The output of the second operational amplifier. V0 of the second op-amp. It is minus of
V minus of minus V in.
R into V in, right? So RR will cancel out, V0 equal to V in. So in the first half cycle we may see that if I will draw the output at here for the case 1, for the positive half cycle of input, I may get a positive response, right? So this is V in and this is V out. So first part is solved. Okay, we have rectified the applied input at the first half cycle. What about the case 2? Now we will see the case 2. In case 2 guys, I'll come back to the circuit again here. Now D1 should not conduct and D2 should conduct. So D1 is off and D2 is on. What will happen to the circuit if this part is not functioning and this is functioning? This part alone means D1, this part alone is not functioning. So this is your RR, all will be in series because this part alone I have taken just the D1 out and D2 is sorted now. So what will happen if you see the next simplified circuit for this one guys? This will be your next simplified circuit. Okay, for case 2 where D2 is on and D1 is off for that case. So let's have a look. If you see the previous circuit, that R and R will become combined because here we have just taken the D1 off and R will become 2R, and as your D2 is conducting, this R will be connected back at the point A, which is linked with your applied input voltage Vi. Okay. So now guys, suppose the V is the applied input at here, and if you apply KCL at this nodal point A, what should be the value with respect to this resistance point, and this resistance point? If you take the first one will be Vi by R. This is V, your V. Suppose you are taking this nodal voltage is V guys. The output of the first op amp is suppose V, and the input is Vi, and the entire output is V naught. Okay, later we will come to this V naught. Now this is Vi by R. The current, if you apply the KCL with respect to point A, we are going to find out. So for this part, if I is the input thing, so what should be the I? This is Vi by R. Then now, as I said, the op amp 1 output is V. By virtual ground, this node will also be the V, because if you see this node and this node both are at the same potential, that's why this will become V. If this is V guys, what should be the current at here? This is V by 2R, because 2R is there, and this point also will show you V by R. So we got all the nodal voltages. One is approaching this side, one is approaching from this side. So all are approaching towards point A. So now we can easily apply the KCL at node A. So what should be the equation? Vi by R plus V by 2R plus V by R. If you equate this, we may get unknown value of V is nothing but minus of 2 by 3 of Vi. So this V, what we have applied at here, which is equal to minus of 2 by 3 Vi. So the next point of simplified circuit of case 2 is this one. Okay, minus of 2 by 3 Vi, which is the input for the next non-inverting amplifier, where the RF is R and Rin is 2R. If you apply the non-inverting op amp concept at here along with this V value, you may get V naught equal to Vi. It will be positive Vi or negative Vi, who will say? Or it is correct only? No answer from your side? V naught equal to Vi or V naught equal to minus Vi? Yes guys?
Minus Vi.
Any other answer? That minus will justify what? Inverting, or it is rectified the negative half cycle also? Already previously we got the positive half cycle is rectified, right? We are waiting to rectify the negative half cycle. This is V in, and we got the V out for the positive half cycle of V in like this. What should we get at here? We may get this one or the dotted one. Solid one or dotted one?
Solid one.
Why not the dotted one?
V out will be positive, like V is equal to minus of Vi. Vi is already negative, so it will become positive.
Yes. Because of that, and that another significance is we have applied a negative input voltage, right?
Yes, ma'am.
And that negative input voltage is giving V in terms of negative. So it is positive now, right?
Yes, ma'am.
So that's why we have to see that, okay, so whatever the initial negative voltage we have applied, after the second interval or after the second stage, it is positive now. Okay, so that's why our output is following the input in terms of the non-inverting input. That's why it will become positive, and we may get a continuity of the fully rectified output in all the half cycles. So this is the working principle of full wave rectifier. Okay, got it guys? Yes or no?
Yes, ma'am.
So in exam guys, directly the question will be not, it will not be carries the word half wave and full wave. The circuit will be given with the diode position. You have to identify the output waveform of the circuit along with the calculations. Means if derivation will be asked, or with respect to the derivation any value will be given, means you have to find out the answer for that. Okay, so this is regarding half wave full wave rectifier. And peak detectors, the next topic guys. This is a circuit, whatever be the circuit condition, if it carries or changing the input from, suppose this is one voltage, this is another voltage, this is another voltage, and like this. Suppose the input is like this. Okay, in this way, suppose your input is there. So this circuit is always capable of choosing the maximum peak. Whatever be the input condition, what is the present input condition, it will compare. If though even though the previous input is high, it will capture that previous. Even though the present one is high, always it will capture the peak output voltage and it will bypass to the output. That is the property of the peak detector. From the construction of the circuit, you can see that this belongs to the precision rectifier circuit, but what we have done, we have taken the feedback from the output only. So like the property is very similar with your precision rectifier, but what we have done, additionally we have connected the capacitor, because this will only identify what is the output at here. This point will decide, and this will make the capacitor to charge. Whenever the positive voltage will appear at here, then only the capacitor will charge. So always this capacitor will decide what should be the output. Okay, so if the capacitor is charging, at that time we may see that, okay, the peak voltage has been detected. If not so, it will get discharged. So this is the property of the circuit. You can go through it, you can study by your own also. This is very simple circuit. Directly the question will not come that identify the peak detector circuit, how does it function out. By the property of the op-amp and capacitor, when the diode will conduct, at that time whatever the voltage across the diode, it will reflect at the capacitor. In this way only the circuit will always behave to identify the peak value of the applied input voltage, and that will be reflected at your output. So these are all application of diode by using your operational amplifier. In next class only we will study that logarithmic amplifier, or maybe if I will take voltage regulator, up to that only your syllabus will be fixed. One topic I will take after the CAT, not the whole unit 3 will come. Module 1, module 2, and maybe tomorrow I may, not tomorrow, in next class I may take the voltage regulator. Up to that, your log and anti-log amplifier will not come. Just you keep in your mind application of that by using op-amp. Up to that only it will come. Okay.
Ma'am, in today's DA, we have a question on voltage regulator, ma'am.
That you have to solve guys. You cannot say that if I will not take the topic in class, you cannot solve that. You may go for your self exercise. Okay. Okay, guys, for today's class, if you don't have any doubt, you may give your attendance as present in the chat box and you may leave.